All right. So what is a secant? We've discussed this already. It's a, for our purposes anyway, a line segment connecting 2 points on a curve. As the 2 points approach each other, the secant becomes a tangent. All right, so as the 2 points approach each other, the secant becomes a tangent. There's 3 ways that that can happen.
Is it possible that in some of the packets, like, it skips over pages? I don't have 5-6. This was 4-7.
There was an issue with the copier, so there might be some loose pages missing somewhere. I think I have a spare of that. Folks, I have digital versions of this online. So if you thumb through your packet and notice that there's some pages missing here or there, just go to my website and print off the appropriate pages. All right, so the 3 ways that this could happen. So I'll give 3 arbitrary curves. Each with 2 points. All right, so those 2 points can actually literally approach each other. So they could both be on the move. That's a pretty rare instance, but they're approaching a single point. It could be the case that the second one is approaching the first one, or it could be the case that the first one is approaching the second one. All right, so we have to be able to somehow account for these 3 possibilities. But fortunately, the algebra approach isn't really overly challenging when it comes to that. It's really when we actually apply the limits that we have to make this distinction. All right, so we learned over the last couple of days that we have 2 different types of difference quotient. The limit as h approaches 0 of f of x plus h minus f of x all over h, where h cannot be equal to 0. If h is equal to 0, it would be undefined. The other possibility is that we have the limit as x approaches a of f of x minus f of a over x minus a. Now, that's only undefined if x is equal to a, so I want to stipulate that x cannot be equal to a. All right, so these are your 2 possibilities if you're looking to find the slope of the secant line. All right, you can work with this expression without the limit, or you can, oh, sorry, geez, I screwed myself up. We don't need the limits yet. I'm ahead of myself. Happens to the best of us. Yeah, because we're still talking about secants, right? But as you know, we're dealing with limits when we want to make that secant into a tangent, all right? So these questions are just asking us to find the slope of the secant line on the given interval. So you can pick your poison here. It really doesn't matter. If you want to work with this one or the other one, it really doesn't make a difference whatsoever. It's all going to come out in the wash. In some circumstances, it's easier to work with one as opposed to the other, but it really ends up being a matter of preference in most cases. So for the first one, I'll use the first difference quotient. For the second one, I'll use the second one. All right, so first thing I'd have to figure out is f of x plus h. All right, because if you look at the model, because we worked with this numerically yesterday, but we didn't do it algebraically. It has an f of x plus h, it has an f of x, and it also has an h. So the f of x is given to us. We're good with that. H is going to be part of the ratio. I just need to come up with f of x plus h. So all I have to do there is take my original function, x cubed minus x, and replace each x with the x plus h. All right, because we're just evaluating a function. Just replacing the x with an x plus h. All right, this one requires us to do a little distributive property, which is fun. Or you could use Pascal's triangle. X plus h to the third power is kind of like borderline, whether you want to do it one way as opposed to the other. But for now, I'm just going to give it to you. So we have x cubed plus 3x squared h plus 3xh squared plus h cubed. All right, so that's this piece. From that, I'm going to subtract off the other one. So let me just get rid of this. This should be a different color anyway. So minus x minus h. All right, so a little distributive property. All right, so you could verify that on your own. Use Pascal's triangle, or FOIL it out, x plus h times x plus h times x plus h. But this is what it would expand out to. All right, so if I'm working with the model f of x plus h minus f of x all over h, where h cannot be equal to 0, then I now know what the f of x plus h part is. It's that whole beefy expression. So I have to write in all that beef. So x cubed plus 3x squared h plus 3xh squared plus h cubed minus x minus h. Then on top of that, I have to subtract off my original f of x. That original f of x is x cubed minus x. I agree. It's pretty gross. All right, it'll clean up a little nicer, and when we do apply a limit to this, it'll get even nicer. Shockingly nice. But for now, it's going to look pretty nasty. All right, so we have some terms that'll cancel out. If your f of x doesn't cancel out completely, then you made a mistake somewhere. It should cancel out with parts of your f of x plus h. So 3x squared h plus 3x h squared plus h cubed minus h all over h. Each term has an h in it, so divide it out. Divide out an h from each term. And there you have it. All right, and it doesn't seem overly useful, but there's something valuable in that. And again, when we get to the limit component of this, it'll become even more meaningful. Right? But our whole goal here is to come up with an expression that we could use to find the limit at any point along the function. Right? So, I'm sorry, not the limit, the slope of the secant between any 2 points along the function. I'm still getting ahead of myself for some reason. All right, so this, believe it or not, is your final answer. And this concept should look very familiar because in pre-calc and gap, this was something that you did. And it was very unsatisfying then and very unsatisfying now. It's like, we did all this for what? What is this telling us? You'll find out in calc. Well, you'll find out in like 5 minutes. All right. So in number 2, I'll use the other approach because I can't even imagine trying to do the x plus h substitution with that rational function. That does not look overly appealing. So let's find the results of f of x minus f of a over x minus a. And again, the choice of which version of the difference quotient you use is entirely up to you. You may decide that you want to use one and then get 2 steps in and realize, well, that's not working out very nicely. Let me give the other one a shot. All right? So let's try this way. And if it ends up being too ugly, we'll switch over. That being said, it's not going to be as ugly as the other way, so I'm only really just saying that. I'm not switching over. All right, so f of x is your original function, reproducing it right here. F of a is the same thing as your original function, just replacing all the x's with a's. Everything else is just built in, so the x minus a, that just comes along for the ride. The thing that's very unappealing about this approach is that you have to do some algebra. So it means you have to do like common denominators and keep, change, flip, and things like that. All right, so you just got to kind of just grin and bear it. Top and bottom by a squared minus 4. So I could FOIL out these guys. I'm going to get a squared x. Outer will be negative a squared minus 4x plus 4. Minus, I'm just carrying down that minus. And I'm going to FOIL these against each other.
Are you distributing it out?
Yeah. Well, yeah, let's not say that in class, Nick. And yeah, you know, let's just talk at the end of class and have a quick conversation about that. It's not gonna fly. All right, so FOIL out these guys. Ax squared minus 4a minus x squared plus 4. All right, we'll clean all, well, I mean, at least we'll try to clean it up in a minute. But the bottom is going to be all of this mess. And if we treat this x minus a as x minus a over 1, we would keep, change, flip that right into this denominator. Keep, change, flip?
So for which part, what part did you keep, change, flip?
I'm keeping this fraction once I put it together,
Okay.
changing this to multiplication and flipping this.
Okay.
Alright. So anything that you could cancel on the fly, you should. like for example, these guys. And then you kind of hope for something else, but unfortunately there really isn't much of anything else. All right, so what I'm going to do is I'm going to rewrite the numerator. I'll distribute that negative to try to clean it up a little bit. But then we have to simplify. All right, the idea being that some part of this denominator should cancel away. Now, it may not seem like it's necessary now. When we do apply a limit to this, the part of this expression that's going to cause the problem will be the x minus a. So right now, there's no context to it, so it doesn't seem like there's any value trying to go any further, but there actually is. All right, so what I need to do is somehow manipulate this expression on the top to allow me to cancel the x minus a, all right? Which doesn't seem like it's the easiest thing in the world to do. I need to basically factor that in some way, that one of the common factors, or one of the factors overall, is an x minus a.
I don't understand why you want to cancel the x minus a.
We're going to find out in the next page when we incorporate a limit.
Okay.
So you just got to wait, yeah. All right, so we're going to look for things that have some kind of commonality to it.
Do you have like a piece of loose leaf scrap paper anywhere?
Yeah, in the back on the table. So, looking at this expression here, you might say something like, all right, I'll pull out the a squared. But if you look at that, all right, so just visualize that. Looking at just these two terms, if I pull out the a squared, what would I be left with? X minus 1. Is that going to cancel anything on the bottom?
No.
So I don't want to group these two together. All right. If I group these two together, I could pull out an x, right? I'd be left with an a squared minus 4.
Yeah.
All right. Well, that sounds like it would be a good move, but that seems to bring us kind of back where we started. If our only goal is to try to cancel out an x minus a, what I want to do is factor out GCFs until I have an x minus a remaining. So I'm going to ignore that one. Let's take a look at this guy and this guy. All right, so a squared x minus a x squared. I could pull out, what would my GCF be between these two terms? An a and a? All right, so pull out an ax, what are you left with?
Just an x.
A minus x, all right, which is the opposite of this, but it's close enough that we can use it. All right, so it's an old school algebra skill, factoring by grouping. But it's one of those things where you work on it a little bit in algebra, and then you don't really do much with it. And then you get here and it's like, okay, remember how to factor by grouping? And you're like, yeah, not really. So, but that's how you do it. Systematically, you're looking for, when you pull out your GCF, what remains to be cancelable with whatever you want to cancel it with on the bottom. All right, so grouping these two together will get the job done for that part. So let's get another pair that'll also do the same thing. All right, so let me see if I can group the negative a squared with something else. That when I do some factoring, actually, no, let me skip the negative a squared because that one might be a little tricky to see. Let's group this guy. So I'm going to write the negative 4x with something else such that it'll have a common factor of either x minus a or a minus x. All right, so if I group it with this one, there is no GCF at all, so that's useless. 4a. Because if I pull out the negative 4, what would I have?
A. Or negative a.
X minus a, which is what I'm looking for. So let's put those together. Right now I'm just concerned with the proper groupings. I'll worry about doing something with that in a sec.
about GCF? Are you just getting rid of the number? Like where are those numbers? Like where are those
I haven't
numbers?
pulled anything out yet.
Oh, okay.
All right, so in the red, what am I pulling out again? An A and an X, and what was left over? A minus X. All right, in the blue, what am I pulling out? A 4, positive or negative? Which one do you want? Negative 4, okay. What's left? X minus A. And the last one, it doesn't look like you can pull out anything, but let me just rewrite it for a sec. Become a little bit more obvious. All right, I'm going to rewrite my denominator. All right, so the blue factor binomial, we're in good shape there. This one's the exact opposite of the way I want it to be. So what could I make my coefficient instead of a positive AX, just gave it away, a negative AX? That would make that X minus A, minus 4 times X minus A. Now plus, this doesn't have a GCF, but it is factorable. What are the factors? X minus A and X plus A.
I have a question. Could you just like write it as like x minus a to the 1/2 too? Like, does that work or no?
No.
Or I mean, not just like never mind.
All right, so instead of actually showing the GCF being taken out now, we can recognize that there is an X minus A across the board in the numerator and one in the denominator as a factor. So we can just cancel it on the fly, which is a little bit nicer than writing yet another step. I'm gonna go green. So on the top, I'll have a negative AX minus 4 plus X plus A. And on the bottom, just an A squared minus 4 and an X squared minus 4. And that's the answer for now. All right, so the tangent we know. In terms of a definition, I think we're kind of beating a dead horse if we write it in words. A description, a visual description is perfectly fine. So, limit definition of a derivative. It would be the limit as h approaches 0, so this is what I wrote on the previous page before I realized I put the limit in, of f of x plus h minus f of x all over h, where h can't be equal to 0. The alternate definition. So basically the pre-calc definition, the difference quotient that we had on the previous page, but now we're applying a limit as horizontal distance shrinks down to 0 between the 2 points. So the limit as x approaches a of f of x minus f of a over x minus a, but x can't be equal to a. All right, that's the condition there, because if x and a were the same in the original function, the difference quotient of it would not exist and be completely meaningless. All right, but x can approach a, just can't get there. All right, so in number 3, when I say the instantaneous rate of change, that's the same as saying find the slope of the tangent. Now, on the previous page, we did all that f of x plus h business. We did all the hard work. So all I need is the limit now as h approaches 0 of this guy, 3x squared plus 3xh plus h squared minus 1. All right. This is my justification. This whole idea here is telling me that limit component, that was telling me that the h had to go in my original expression. That's how I knew that I had to keep going until I was able to cancel out that h. Because at any point, if I evaluated this limit for h equals 0, I would have gotten something undefined. And in these cases, the limit will always be defined. All right, we'll deal with some situations down the line where it's not, but we're not there yet. All right, so if I apply this limit, basically replacing all h's with 0, what do I get? 3x squared minus 1. All right, and what this represents is the slope of the tangent line at any x value. So thinking back to the activity where you filled out the whole table, you noticed trends, you hope that it converged on a particular value like -6 or +1. What if you don't recognize the relationship? What if you don't recognize the trend? You may never be able to come up with a derivative that way. What you get from this is a function that, as long as you know what the x value is, you'll always be able to determine the slope at a particular point. So I now know that if I need the slope when x is equal to 0, that slope will be -1. So you could graph this, put a ruler on it at the x value of 0, and you'll see that it'll at least look like it's a -1, right? And that'll work no matter where you put your ruler. As long as you can identify a particular x value, you can pop it in there, and then it'll tell you what the slope is, all right? The next one is not, unfortunately, the second example. What happened there? Ooh, I don't like that. This should be, what was the original problem?
X minus 1 over x squared minus 1.
All right, so using the same, if somebody wants to submit that as a typo for bonus, you can. Limit as x approaches a of this beast.
Oops, send it. You guys are off. So, no, I'm just kidding.
So if we're using the alternate difference quotient, we go through the whole process, simplifying like we did, we come up with this expression. And the question was, how would we know that we needed to try to cancel out the x minus a? Well, we would know because if x minus a was part of this, then when I go to apply the limit, it gives me undefined, just like in the previous one. So that had to go, that drove the approach that we took. Now what we can do is apply the limit. Now this is one of those interesting situations because if x is approaching a, if x ever got to a, then what that would mean is that x and a would be the same. All right, it would be equal to a. It's not going to be equal, but it would be if you could get there. All right, that makes x and a interchangeable. So what it tells me is that I can replace any of the x's with a's, or I can replace any of the a's with x's. It all depends on what you're looking for. Right? If you're looking for an algebraic expression that represents the slope of the tangent line, then you want it in terms of x. But if you're doing it numerically, so at a particular point, then you want it in terms of a, so you can replace the a with a number. And at the end, it really doesn't make much of a difference, because if you're plugging a number in the final step, who cares if you're replacing the a with the number or an x with a number, right? So we'll come up with a function here. I'm replacing every single a with an x. So negative x times x minus 4 plus x plus x. All right. So x plus x over x squared minus 4 times x squared minus 4. All right. So that cleans up to negative x squared plus 2x minus 4 over x squared minus 4 squared. All right, so this expression represents the slope of the tangent line at any x value. Just because we use a different difference quotient doesn't mean anything. They both give us the same result. Now, if I want to determine the slope at x equals 1, now I'm going to replace all of those x's with 1's. All right, so I have a negative 1 plus 2, which is positive 1, minus 4 is negative 3. On the bottom, I got 1 minus 4 is negative 3 squared is 9. So we're looking at negative 1/3. You know, what is a normal? It's normal. But by definition, it's the equation of a line that is perpendicular to the tangent of a curve at a given point. Page 6 again, folks. So if I'm looking for a normal, I'm looking for something that's perpendicular. That line looks terrible, so hold on. This one's not going to be much better, but I don't know. It's an attempt at highlighting. Somebody told me that they had a sensitivity to the color yellow, so I'm not using that as a highlighter anymore, but the obvious drawback to that is it doesn't look very highlighted. So it is what it is, as Mr. McCauley would say. Anyway, what does it mean when slopes are perpendicular to one another? Slopes are what? Just reciprocals? Opposite reciprocals, negative reciprocals? All right. The correct term in textbook lingo is negative reciprocal, but opposite reciprocals tells you more so what it is you're looking for. So we'll go with that. All right, so that means that we have to do all the work that we did in order to come up with a derivative. And then once we have the derivative at the point, we have to find the opposite reciprocal of that. All right, so let's work with the one I prefer, because the reality is this is all about me. That's not true. I mean, it's mostly true. It's this one because this is the easier one to work with in almost all cases. And the only reason I say almost is because I have not thought of a case where the other one is easier to work with. So maybe when we get to trig, I'll change my mind. But even then, I still think you can get away with this one. Yeah. All right, so my f of x is given.
Do we always have to write limit approaching x approaching a for each
Yeah.
thing?
Yeah. Anytime you have a limit problem, you always have to include the limit statement. Seems nitpicky or ticky-tack, depending on what kind of archaic language you like to use. But yeah, it's got to be there, otherwise it's not proper. All right, minus f of a, which is what you get when you replace all the x's with a's. All over x plus a. Sorry, x minus a. I don't know why I said plus. Constants should cancel out if you're doing this right. So the 9 with the 9. And then I guess maybe frustratingly nothing else. The one thing about the other approach, the x plus h one, is that much of it will cancel out, and that's a good thing. But what'll happen is the amount of work that it takes to get to the point where you can cancel a bunch of things out makes it kind of not worth it. All right, so that's why I like this approach. All right, so the more complicated the original function, the more involved the factoring step will be. But once you get here, there will be a factoring by grouping technique that you could use to help you simplify things down. The idea being that you want to have a common factor of x minus a. If you have a common factor of x minus a, then you'll be able to cancel out the x minus a on the bottom, and then you'll be able to apply the limit. No, it's okay. There's like 10 more sharpeners in this wing if you want to test them all out. So, we want to group it in such a way that we get a common x minus a. So, the way it was originally formatted doesn't really make much sense. I don't want to keep the original groupings, because here if I pull out an x, I'm not going to have any a be part of it. Here if I pull out an a, I'm not going to have an x be part of it. So we want to start rejiggering it a little bit. These two make sense to go together, because if I pull out a -3, I'll have the x minus a. And at this point, it's really just a matter of, I don't like to overuse the word perseverance, but that's really what it is. Because if you try each and every combination of terms, if you try each and every one of them, eventually you're going to come out with the appropriate arrangement. All right? You just hope to not have to try each and every one. It's kind of like rational root theorem with synthetic division. You have that big long list of p over q values. The hope is that it won't be the last one that works. You'd like to get to the one that works way before that. So you look for things that are in common. Here we have a common coefficient, so it's a good place to start. I pull out the -3, I'm in good shape. The x squared minus a squared, it's not a matter of a GCF there. That's a matter of factoring the binomial. All right. So really, I mean, if you follow the traditional pathway, you know, algebra 1, geometry, algebra 2, pre-calc, you had 2 years of algebra really for a reason, and that reason is for you to be able to handle these last 3 steps. All right. That's why you have all that practice. You start off slow with like GCFs and difference of squares, and then you kind of increase until you get to the more complicated stuff, so that stuff like this isn't completely foreign to you by the time you get here. Anyway, this next step, instead of actually factoring out an x minus a, I say, well, I have an x minus a in each term of my fraction, so we'll do the, you know, a little shorthand cancellation. So I have a -3 plus x plus a. And the idea, again, is that if I apply the limit, that's telling me that a and x are getting really, really close to one another. If they get close enough that there's basically an infinitesimal space in between the two, then we can think of a as being equivalent to x and x being equivalent to a, right? So the amount of space that's in between x and a is so negligible, so teensy tiny, that we can think of x and a as being at the same location. Right? They're not exactly the same location, but we can think of them as being at the same location. That gives us license to replace any a with an x through substitution, or replace any x with an a. Most people prefer to replace the a's, so you have an answer in terms of x. That's just direct substitution. And so we get -3 plus 2x. Where did it go? All right, that's our derivative. That we call f prime of x. All right, also represents the slope of the tangent line. Right, so no matter where x is along the curve, I can now have an expression that will give me the tangent line's slope at that point. So, I mean, we could graph the curve itself, but just to have an arbitrary curve here, I can have any one of these points, any point, but these are the ones I'm creating in particular. That would be a tangent line with a slope, so would that, so would that, and so would that. Each would have a different slope, right? Each line segment is pitched at a different angle. So if that's the case, depending on what the x values are at these locations, so x1, x2, x3, x4, I can now figure out what the slope is based on that expression.
How do you know that x and a are close enough that they...
Because x is approaching a. It's kind of like when x is approaching infinity, we're assuming that x is getting out close to infinity. What's happening out there? Right. That's how one looks at it. All right, so now what I need to do is find the normal to the curve at x equals 0. So first that means I have to find the slope of the tangent at x equals 0, so I'll find f prime of 0. Which is -3. That's the slope of the tangent line. So the slope of the normal which is going to be perpendicular to that slope, would be the opposite reciprocal of that, so +1/3.